Welcome. We will look at this differential equation. We will learn how to solve it. So this is a second order differential equation. And we will just like learn how to solve it. And remember, like to solve these guys, we just integrate them. So giving the governing equation of a steady state flow equation for unconfined aquifer with recharge. So this is recharge, this is hydraulic conductivity, and find H. We want to find the head as a function of distance. So at like different. So let's say you have like there's a river here and another river here, and you have a head here and another head here, and then we want to see like with recharge. Without recharge, you will, so like you have a river here, yeah, and a river here, and here is, let's say your, ah, here's as your aquifer. Okay, but with recharge, you will get something that looks like this, and you will have like a groundwater divide where part of the water will flow here and other part of the water will flow here. Okay, if you remember this problem, and the boundary condition is given. So here at this guy, the boundary condition is giving as like H1, and here at, so this is like your X, and as X equal to 0, you get H1, and as X equal to L, you get like H2. Okay. So as X is equal to 0, you have H1, and so these are your two boundary conditions. And you got like here H2. That's like, this is H2, and this is H1 at X equal to 0, here at X equal to L. Okay, so can we integrate this guy to find like H as a function of X? And with giving like, so giving that, so you say like your boundary condition, you write your boundary condition, so X equal to 0, H is equal to H1, at X equal to L, H is equal to H2. So solve this guy giving this boundary condition. Yes, we know how to do this, yeah? So basically you integrate here d2h square over dx square negative 2. You can take this out. The recharge is also constant, so you can also take the recharge out, and wait, recharge is constant and k is constant also, yeah. So that is here like dx, and you integrate. So you integrate this guy with respect to dx, and you integrate this guy here, negative 2wk, also with respect to dx. Charge is constant, so you have some recharge here, w, That's constant. The hydraulic conductivity here, just like your hydraulic conductivity is as constant. Okay, so the integration of this guy basically with respect to dx, remember this guy, you here you have the second derivative, and then like you integrate, then you get your basically your first derivative. Yeah, so we have, so that would be the h square. Yeah, and here what you get here, you get the integration of this guy, that would be negative 2w k x. The integration of this guy would be x plus constant. Yeah, because remember, like this guy reverse this guy, so if you want to get rid of this guy, you get rid of one of these guys, so you get something like this. Yeah. Okay, so now we did our first integration. So what do we do? Well, we just do the same thing. Yeah, we integrate uh, we integrate this again. Yeah, so basically like we just do the same thing. So here we integrate this guy here with respect to dx is equal to the integration of this guy here with respect to dx. Let me just call this C1 because I know we'll get another one of these, yeah? So again, similar here, like these two guy will like reverse this guy. So all these guy will get rid of one another, yeah? Oh, sorry for this mess. So this guy will reverse this guy. So what do you get here? You get like h squared. And what do you get here? So what you get here, you get negative negative 2wk x squared, and then I divide by 2 here, plus c1x plus constant 2. I get another constant. Okay. Okay, so we have an equation that now looks something like this. So we are done. Let me clean this a little bit. I can remove this guy with this guy. Yeah, so I have an equation that looks something like this. We are almost done. We just need to substitute for our boundary condition. So here we can say for x equal to 0, h is equal to h1. So can we do this? Yeah, you can do this. So let's do, so here I have h1 square, that would be 0, that would be 0, that would be c2. So c2 is equal to h1 square. Okay. Now, can we use our second boundary condition? Yes, we can. For x is equal to L, we have h is equal to h2. So now we can say like h2 square is equal to negative w over k. X now is equal to L. So I have here x square, so that would be L square. Yep, sorry. Plus C1L plus C2, that is H1 over 2. Yeah, so we have something now that looks like this. So can I do something here. Yes, I can do something here. Minus h1 square plus w over k l square that is equal to c1. Here I have c1l, so I will just divide all these guys by L. Yeah, so if I divided all these guys by L, I can simplify this a little bit further. So I can say like this guy minus this guy over L plus WK over L, that's equal to C1. Yeah. Okay, so now I substitute C1 and C2. I substitute them here. So can we do this? Let me just try to do this substitution. Yes, I can do this. Yeah, so I can say like H2 negative WK x squared plus C1, which is this guy here. That's like H2 minus H1 over L time X. Yeah, because this is time X here. Plus WK L time X. Yeah, plus C2. That is H21. Yeah. So I got an equation that looks something like this. Can I rearrange some of these terms? I think I can. Like for example, I have this guy here and this guy here. So I can take I have this guy here. The most obvious thing is I just bring this guy at the beginning, yeah? And then I have this guy here. I cannot do much with this guy, so I can just say this is plus negative h over 2 over L time x. Yeah, so I cannot really do h. Yeah, so I cannot really do here. That's like h. Yeah, do much with this guy, but here, like these guys, I can do something with them. So I can say plus w over k, and that will give me w over k L minus x time x. Yeah. Yep. That will give me something like this. Okay, so I'm done. Yeah, I'm done actually. I can just, instead of having h square, I can get rid of this square, and I can say this is like be equal to the square root of. Oh, it looks horrible. Okay, something like this. Okay, so I have h here. I got like this relationship. So if I will check my answer here, yep, check this guy here. I got something similar. Yeah, I got something similar. So h as a function of x is equal to, yeah, see this guy here, see this guy here, and this guy here. So what does this mean? Let's just see the meaning of this, yeah. So here, this is just like if you want to use this equation, because you have an equation which you can use. So basically, that is like your river one, so that is the head in this river here, that is like the other river here, that is the head in this river here, and that is when you have no recharge, like when you have no recharge, like basically like this term will go away, and you basically see this non-linear relationship. Head here is high, head here is low. So what happened is that flow go from high energy, from high head to low energy. So you'll see like flow going in this direction here. So that'll be like the flow direction here. Okay. But now uh, when you have some recharge, so like here you have two values of recharge. Here you have a larger recharge, which would be like this guy here, and here you have a smaller recharge, which would be like this guy here. And if you have a larger recharge, you will get, see here, this is a groundwater divide here. So basically, like you see, the head will increase until it reaches a point, and then it will decrease again. So here you'll have a groundwater divide. Head here would be higher, so you will have a flow from here to here. That would be like a groundwater divide, and then you have another flow from here to here. If you have like a smaller recharge, that would be here. So you'll have like some flow from here to here, and most of the flow would be from here, like here, sorry. If you have like, so the groundwater divide will be here, and you have some flow will go here, and some flow will go here. And you see here, that is like your H maximum, like your head maximum for the high recharge would be 11.55. So that's like your maximum head that you get would be here at like this point, and that is about 11.55. Your maximum head will be here at this point, and that would be about 10.21. So that would be about 10.21. And that's like a groundwater divide. That is a groundwater divide. So water will flow from here to here. That's a divide, yeah, and water, and so on. Okay, so that's basically like this problem, and I will like see you in the next video.